Section 1. A New Dawn on a Red World. Imagine a sunrise unlike any you have ever known. The light is not gold, but a soft, dusty rose. Ochre plains and colossal silent volcanoes. Human footsteps pressing into fine red soil. Towns beneath vast, transparent domes. Sprawling farms and subterranean tunnels glowing with life. A vision once only dreams. Yet in the year 2025, that dream inches closer, propelled by technology, ambition, relentless human curiosity. 2025 is a critical pivot point with decades of robotic reconnaissance culminating in a plan for human exploration. The knowledge gathered is no longer just academic. It is becoming a practical blueprint for survival. This essay will chart a course through this era. We will explore the state of our Martian endeavors today. We will trace a plausible timeline for coming decades, outlining key technologies that will make the journey possible, and confronting the monumental challenges ahead. The journey to Mars is not just about planting a flag. It is about understanding our place in the universe and securing the future of our species. So, let us begin this exploration. Section 2. The Lure of Our Celestial Neighbor. Why Mars? Of all the celestial bodies in our solar system, why does this one cold, distant world hold such a magnetic pull on our collective imagination? The answer is both practical and profound. Mars is quite simply the most Earth-like planet within our technological reach. It possesses a day and night cycle, a soul, that is remarkably similar to our own, lasting just over 24 hours. This familiar rhythm makes it more hospitable for the biological clocks of future human explorers. The planet also has seasons, driven by its axial tilt, just like Earth, offering a predictable, albeit much colder, pattern of environmental change we can learn to work with and harness. Beyond these surface similarities, Mars holds the most vital ingredient for life as we know it: water. We now know, thanks to decades of robotic exploration, that vast quantities of water ice are locked away in its polar caps and buried just beneath its dusty surface. This frozen reservoir is more than a scientific curiosity. It is a critical resource. Water can be melted for drinking, used to grow crops in protected environments, split to produce breathable oxygen, split to produce rocket fuel. The presence of water transforms Mars from a barren rock into a world with potential. A place where a foothold for humanity might be possible. Section 3. The Robotic Vanguard of 2025. As of this moment in 2025, Mars is a bustling hub of robotic activity. It is a world populated not by humans, but by their incredibly sophisticated emissaries. These rovers, landers, and orbiters are our eyes, ears, and hands on the red planet, tirelessly working to unravel its secrets and pave the way for our eventual arrival. They are the unsung heroes, conducting the critical reconnaissance that makes human missions conceivable. Their data streams back to Earth in a constant flow, painting an ever clearer picture of the Martian environment, its resources, and its hazards. This robotic fleet is the front line of human exploration. Circling high above the rust-colored surface is a constellation of orbiters from multiple nations, each with a specialized role. They act as planetary cartographers and as meteorologists. They map the terrain in stunning detail, identifying safe landing zones and spotting potential resource deposits like buried water ice. They monitor the thin atmosphere, tracking dust storms and measuring temperature swings. Crucially, these orbiters also serve as communication relays, creating an interplanetary internet for surface assets to phone home. Down on the ground, a new generation of rovers crawls across the alien landscape. These mobile laboratories are geological detectives, equipped with advanced drills, spectrometers, and cameras. Section 4. A Cosmic Roadmap. Humanity's Next Giant Leaps. The path from our current robotic presence in 2025 to a thriving human settlement on Mars is long and incremental, best understood as a series of carefully planned phases. This timeline, often discussed by space agencies and private enterprises alike, provides a logical progression with each step building upon the successes of the last. The remainder of the 2020s will be defined by an intensification of our robotic efforts. We will see more sophisticated rovers, more powerful orbiters, crucial technology demonstrations, landing ever heavier payloads, and refining methods for producing oxygen and fuel directly from Martian resources. This is the foundational phase of preparation. The 2030s will likely mark the dawn of the human Mars era, though it will begin with machines. This decade will see the launch of massive cargo missions, robotic freighters hauling essential infrastructure. These payloads will include habitats, solar or nuclear power systems, life support equipment, and the vehicle's crews will need to explore the surface. Following these cargo drops, we may see the first short-duration crewed missions. These would be boots-on-the-ground missions where astronauts land, stay for a few weeks or months to activate the pre-deployed systems, and conduct initial experiments, then return to Earth, proving that humans can indeed live and work on Mars. As we move into the 2040s, the focus will shift from short visits to long-duration stays. Astronaut crews will begin to inhabit Mars for missions lasting a year or more, aligning their stays with the planetary launch windows that occur every 26 months. It is during this decade that the first permanent base will truly take shape. This outpost will grow modularly, with each successive mission adding new laboratories, living quarters, and industrial capabilities. The population might grow from a handful of pioneers to a dozen or more, researchers, engineers, technicians, forming the nucleus of the first off-world human community. Beyond 2050, we enter the era of true settlement. The initial base will evolve into a larger, more complex settlement with a population living on Mars year-round. We can envision the development of extensive greenhouses for agriculture, factories for manufacturing spare parts and building materials, and the expansion of habitats to accommodate a growing community. The goal during this phase is to move from reliance on Earth to robust self-reliance, creating a sustainable presence that can weather interruptions in the supply chain. This is the point where Mars begins to transform from a remote scientific outpost into a genuine second home for humanity. Section 6. Confronting the Great Martian Challenges. For all its promise, Mars is an incredibly hostile environment, and the challenges to establishing a human presence are monumental. The first and most obvious is the sheer distance. The journey to Mars is not a quick trip. It is a grueling 6 to 9 month voyage through the vacuum of space. This long transit time exposes crews to significant health risks, including muscle atrophy and bone density loss from zero gravity. It also creates a communication delay of up to 24 minutes each way, meaning that in an emergency, there is no Houston, we have a problem with an immediate response. Astronauts must be trained to be completely autonomous. Once on Mars, the greatest invisible threat is radiation. The red planet lacks a global magnetic field and has a very thin atmosphere, leaving its surface exposed to a constant bombardment of galactic cosmic rays and energetic particles from solar storms. Long-term exposure to this radiation significantly increases the risk of cancer and other health issues. Therefore, habitats must be heavily shielded. This can be achieved by using thick walls, burying habitats under several meters of Martian soil, or situating them inside natural lava tubes. Likewise, astronauts on surface excursions will need advanced spacesuits and shielded rovers to minimize their radiation dose. The Martian climate itself presents another set of formidable obstacles. The average temperature is a frigid -62 degrees Celsius, -80 degrees Fahrenheit, and the atmospheric pressure is less than 1% of Earth's. Any machinery or habitat must be designed to withstand these extreme cold temperatures and the vast pressure difference. Furthermore, the ubiquitous fine red dust is a major hazard. It is abrasive, electrostatically charged, and can get into everything, potentially damaging seals, clogging mechanisms, and posing a respiratory risk to astronauts if brought inside the habitat. We must develop technologies to mitigate dust and keep our systems running smoothly. Finally, there are the immense logistical, financial, and psychological hurdles. The cost of a Mars program will be astronomical, requiring sustained international cooperation and political will over many decades. The logistical challenge of transporting and maintaining all the necessary equipment is a puzzle of epic proportions. And we cannot overlook the human factor. Confining a small group of people in a small habitat, millions of miles from home, for years at a time creates immense psychological stress. Selecting the right crews and providing them with the psychological support they need will be just as critical as engineering the rockets and life support systems. Section 7. From outpost to colony, the path to permanence. The very first step is site selection. Future missions will need to land in locations that are not just safe for landing, but are also rich in resources. Subsurface water ice, ample sunlight for solar arrays, canyon shelter, lava tube shelter. Choosing the right spot is the first move in a long game of survival. The second, and perhaps most crucial step, is to aggressively implement local resource utilization. The mantra for early settlers must be live off the land, deploying and scaling up ISRU technologies tested in earlier missions, extracting water from ice, generating oxygen from the atmosphere, producing methane for fuel. We must also learn to use the Martian regolith as a building material, sintering regolith into bricks, using regolith as aggregate for concrete, constructing habitats, building radiation shields, laying roads, creating landing pads, dramatically reducing reliance on materials shipped from Earth. Power is the engine of civilization. A Martian settlement will need a powerful, resilient energy grid. Large-scale solar farms with robotic dust cleaning systems, reliable nuclear fission reactors for baseline power. Abundant energy unlocks everything else. Large-scale mining operations, advanced manufacturing, climate-controlled greenhouses for food production, power to support a growing population. A robust power infrastructure is the non-negotiable foundation for a Martian society.